Okay, welcome to lesson 2 on potentials and thermodynamics of cells. The first thing we want to discuss is how are we going to understand what electrode potential is? What is this potential? A simple understanding of it is that it's a measure of the energy of electrons inside of your electrode. And so we can ask, well, what happens when this energy changes? What happens if it becomes more negative? Well, if it becomes more negative, then the energy of those electrons may become more energetic than those in your solution, specifically in the unoccupied orbitals. And so you might have a high energy electron from your electrode jump into an unoccupied orbital in your solution. That's what we term reduction. And then what happens if your electrode becomes more positive? Well, then we might see an oxidation occur, where an electron, a high energy electron from your solution, jumps into a lower energy state of your electrode. So there's a basic understanding. Let's dive into the details a little bit more. So if you recall from your any chemistry classes that you've taken before, there are orbitals that electrons occupy. And these orbitals, they're governed by quantum mechanics and also by a principle called Pauli's exclusion principle, which states that fermions, like electrons, cannot occupy the same quantum state inside of a system. And so what that means is that within every orbital, there's two possible options. We can have a spin-up electron or a spin-down electron, but no more than that. So 2 electrons per orbital. And you can see we then just fill from low energy to high energy, from 1s to 2s to 2p to 3s, and so forth. And so for a neutral sodium metal, there's 1 electron in that 3s orbital. And then in sodium plus, it's lost an electron because electrons are negatively charged, making it Na plus. And then as that electron leaves, there's a reorganization of energy because the electrons in these orbitals, they do affect each other. So what happens when we go from 1 sodium atom on the left into, say, a metal, a bulk metal, like what we might see in our electrode? Well, in this case, these energy levels, specifically the upper energy levels, the valence energy levels, they kind of merge together between all of these atoms. And what we end up with is a valence band at lower energy states and a conduction band at higher energy states. And as electrons move through some metal, some conductor, they're moving through the conduction band. And in metals, what we define as conductors is actually when the conduction band and the valence band overlap, and that makes it very easy for electrons to travel through these conductors. Well, what about our analytes? We just talked about metals. What if we have an analyte or an ion with the electron configuration we see here on the left? What happens when we take one of those and then combine it with many other neighbors? Well, what we end up with is, instead of having a valence band and a conduction band, we end up with a probability distribution of energy states. And so what we might see is this 2p from one ion, it will kind of morph and become this blue highest occupied orbital distribution, where there's a distribution of energy states. And this distribution occurs because all of these ions are interacting with each other or with other ions in the solution, and that causes the distribution to occur instead of having a clear-cut energy for each orbital. And then, of course, if that occupied orbital of 2p becomes that blue probability distribution function, well, then we'll also have a probability distribution function of the unoccupied orbitals, like the 3s orbital here. So What if we put in electrode, where we have our valence band and conduction band, in with an analyte solution? Well, then we'll have an energy level here for our electrode, and then energy levels here for our solution, the analytes in our solution. And the way that electrodes work is that we can actually increase or decrease the energy of our electrons with ease. And that's part of what makes electrochemistry so powerful, is that that gives us great control over the redox process. We could, for instance, increase the energy of our electrons to be more negative. And that would cause the energy of the electrons in the electrode to have a favorable path to move into the unoccupied orbitals of the solution. And then, of course, to keep, I guess, a distribution of charge within that atom or that molecule that's reasonable, it might eject an ion that either it was coordinated with or bonded to something of the sort. Now, of course, if our electrode becomes more positive, then we might see electrons from the highest occupied molecular orbitals jumping into the electrode. So what might this look like in real life? Well, let's say we have copper chloride, and the copper is in a 2+ state. When it reduces, it might become a metal. And when it oxidizes, it might gain another chlorine atom that it's coordinated with, and keep its distribution of charge that way. So a few other terms that we want to go over. First, there's reversibility. And there's a few different kinds of reversibility. There's chemical reversibility. That's when the reaction can go both forwards and backwards in both at rates that are comparable to each other. There's thermodynamic reversibility. That's when your change of entropy isn't changing in whatever action or process is being undertaken. Usually the examples given here are, very slow incremental steps is how this reversibility occurs. And then finally, there's practical or electrochemical reversibility. And what we mean by this in electrochemistry is that the Nernst function is properly describes the chemistry occurring at the electrode. And what is needed for that is that your reaction kinetics are fast enough that your potential at your electrode is able to influence the chemistry in your solution so quickly that it always looks like the Nernst equation is in force. A few notes on Gibbs free energy. We define enthalpy as the addition of internal energy and pressure energy, or PV energy. And then we define Gibbs free energy as the enthalpy minus the temperature multiplied by the entropy. And what we can think of as a conceptual idea of what Gibbs free energy could mean is the available energy that isn't lost to entropy. That's why it's known as free energy. So how do we relate Gibbs free energy and potential? Well, it's with this simple equation. The potential is equal to the negative change in Gibbs free energy over the number of electrons that are exchanged in the reaction, and Faraday's constant, which is the number of coulombs that are in a mole of electrons. And so we know that Gibbs free energy is, when it's negative, that indicates that the reaction is spontaneous. So if a negative Gibbs free energy is spontaneous when it's negative, what potential sign would indicate a favorable reaction? Well, it'll be the reverse. So a positive change in potential is the same thing as a negative change in Gibbs free energy, which means that it's a favorable reaction. And we can write this reaction also for a standard reduction potential using standard states. And just like with the rest of thermodynamics, we typically need to have a reference state. So let's talk a little bit more about how we can go from the change in Gibbs free energy to our potentials. Well, first off, we need to define how we're going to say how we're going to define our potential of our cells. So each of our cells, we're going to have a cathode and an anode. There's going to be a reduction occurring at one electrode and an oxidation occurring at the other electrode. And so how we write this is we write the potential of the cell is equal to the potential of the reduction reaction minus the potential of the oxidation reaction. And if you're applying a current through this, then we also need to include the resistance occurring inside of the cell. So we can write this for standard conditions, and we can also write out the Gibbs free energy of a reaction. Say we have A plus B going to C plus D, and here the lowercase letters, these indicate the stoichiometry of the reaction. And so when we write out the Gibbs free energy for this reaction, we have a reference state for Gibbs free energy. And then we have RT and then the natural log of an equilibrium constant. And this equilibrium constant is the activities of the participants in the reaction, and they are raised to the power of their stoichiometry. So we have the activity of C raised to the power of C, the activity of D raised to the power of D, and we do products over reactants. So let's go through a little example here. How would we write this out if we had cerium chloride that was being electrolyzed? And so at our cathode, we have a reduction to cerium metal, and at our anode, we have an oxidation to chlorine gas. Well, we write out the change in Gibbs free energy according to the activities of each of the substances. And so we raise the activity of cerium to the second power because of its stoichiometry, the activity of chlorine gas to the third power for the same reason, and then those are both divided by the activity of cerium chloride to the second power. Well, then we can make our transition to potential by dividing our equation by N and F. And what we end up with is a standard potential. And then we have what you might recognize as the Nernst equation, where we have our products on top and our reactants on the bottom. So let's talk a little bit about how we can define activities now. So for a solid, we say that the activity is equal to the activity coefficient multiplied by mole fraction. For a liquid, we define it as the activity coefficient multiplied by a concentration over a standard concentration. And the typical standard concentration is 1 molar. We can also do a mole fraction in liquids if we want to. For gases, we use partial pressures, and the pressure reference is 1 bar. And then if we have a pure substance, then we say that its activity is equal to 1. So we take our former Nernst equation for the cerium chloride electrolysis, and we start going through and replacing our activities with things that we can measure or correlate, like activity coefficients, pressures, and concentrations. And so I think this might be a typical experiment that we want to do is we want to measure the standard potential for our reaction. And how can we do this? We have so many terms up here in this blue reaction. Well, we can fix some of the terms. For example, we could fix the activity of chlorine to be equal to 1 by having a pure chlorine atmosphere in our reactor. And then we could fix the activity of cerium chloride by either having pure cerium chloride or by having very dilute cerium chloride, because then its activity coefficient will approach 1, and we can just use the concentration of cerium chloride, which is much easier to measure than its activity. Of course, we don't have to worry about the activity of cerium because as it's a pure metal, we can say that its activity is equal to 1. So let's talk about formal potentials. Essentially, the difference between a formal potential and a standard potential is that we've lumped together the activity coefficients of the species into the formal potential. So we've gone from using activity inside of our natural log to using concentrations inside of our natural log. So this is the end of the first part of the video of the lesson, and so I wanted to go over a few examples. Hopefully I want you to try these out. Pause the video, try them out, and then if you play it again in a few seconds, I'll give the answer. Okay, here we go. Here's the answers. So what is the difference between chemical and electrochemical or practical reversibility? Well, chemical reversibility means that you have significant rates of reaction going both forward and backward for reaction, whereas electrochemical reversibility is all about the Nernst equation being valid at the electrode. And the second question, what kind of variables make up the formal potential? Well, if we write out the Nernst equation and then we lump together the terms that don't make it into the expression that includes the formal potential, we can see that the activity coefficients and the temperature are included in the formal potential. And so, if you were using a tabulated value for your formal potential and you had reason to believe that you were working under a different temperature or with a different activity coefficient, then you would have to make some adjustments to your measurement in order to account for this. Okay, well, we hope you'll join us for our next sub-video under this lesson on reference electrodes.